And so as I mentioned earlier, with ionic charges, the main group cations, and I'll go ahead and again write those. We're talking about group 1 or 1A, group 2A, and group 3A. So for your main group cations, the charge of the cation is equal to the group number. So group 1A is +1, group 2A is +2. And the reason is because when it loses one electron, it becomes like the preceding noble gas. So all of your group 1, group 2, and group 3A elements, when they lose enough electrons, they become like the preceding noble gas. That's why metals like to lose electrons, at least the main group we're talking about. Now for your anions or monoatomic anions, such as groups 5A, 6A, and 7A, if you take the group number, and there's different ways you can do this, I'll mention two, but if you take your group number that you're on and subtract it from 8, that'll tell you the charge of the anion for that group. So if you take 5 minus 8, you get -3, so -3 is the charge of group 5A anions. If you take 6 minus 8, that's -2, and you see that everything in group 6A has a -2 charge when it's an anion. And then lastly, the halogens, 7 minus 8 gives us -1. And so you see fluorine all the way down to iodine have a -1 charge for their anions. So this is one way you can remember the charges of the main group ions. Another way you can look at it is you see nitrogen is 3 away from the nearest noble gas. So since we have to add 3 electrons to become like to have the same number of electrons as the nearest noble gas, since we added 3, it gets a -3 charge. And so these are different ways that you can kind of remember the charges of the monoatomic cations and anions for the main group. We're not talking about transition metals or the post-transition metals. We're just talking about main group ionic charges. Now for the transition metals, there are only 4 transition metals that we're going to mention that only have one ionic charge. And that's going to be scandium here next to calcium, which has a +3. And the reason I'm telling you this is because since scandium is only a +3, you don't have to include the Roman numeral when you write a compound with scandium. And the other 3 are zinc, silver, cadmium, shown here. So if it's a transition metal that's not one of these 4, you can assume that it's going to need a Roman numeral. Because if it's not one of the 4 I just mentioned, they're going to need a Roman numeral when you write the ionic compound. Now for your post-transition metals, there are 2 of them that have multiple ionic charges, and these are tin. Let me use a different color. These are tin and lead. So tin and lead, you have to include the Roman numeral when you're writing the ionic compound. And this to show you a variety of different charges. So scandium is +3, but chromium can be anywhere usually from +2 to +6. Cobalt usually +2, +3. Nickel +2 and +3 as well. So you see a lot of these, such as iron, cobalt, nickel, copper, gold, mercury, tin, and lead. They have 2 different ionic charges. They have a high charge and a low charge. So remember that, that's very important. So these transition metals that have a high charge and a low charge, which means they have 2 ionic charges, there's actually an alternate or a common way to name these. So again, those are the ones underlined in yellow. So iron, cobalt, nickel, copper, gold, mercury, tin, and lead. These have what we call a high charge and a low charge, so 2 charges total. The other transition metals do not. And so in a second, you'll see the alternate way to name these. So my recommendation is don't try to kill yourself memorizing all the different charges of the transition metals or post-transition metals. If you just know the main group anions here, get the brown. If you know these, then you can deduce the charge of the transition metal. So it's important to know what I highlighted in brown, and of course the main group cations as well. But if you want to memorize them all, feel free to do that too. So in the previous lecture I posted, I showed how to name compounds that have one ionic charge. So now we're going to look at ionic compounds with cations that contain more than one charge. So it's very important to mention it. Just to give you an example, iron 2+ and iron 3+, just one electron difference has a big difference in their chemical and physical properties. Iron 2+ is highly reactive with oxygen. So when oxygen touches iron 2+, it forms iron 3+. So the different charge on the metal means it's going to have different chemical and physical properties for those compounds. So now when we're referring to transition metals, again, we're referring to the ones I mentioned earlier, group 3 through 12 on the periodic table, and these are the ones that are the exceptions. So these you do not include a Roman numeral, these 4. If it's any other transition metal, you include the Roman numeral. In addition to the transition metals, if you have, as we mentioned, lead or tin, you need to include the Roman numeral. If it's any other post-transition metal, it just has one charge. So now here we have CuCl. You may be like, hey, I don't know what the charge of copper is, but you should know the charge of chloride, and once you know the charge of chloride, you can determine the charge of copper. Because what happens is that when you add up the total charge from the cation and the anion, it has to equal 0. So if you know that the charge of chloride is -1, you can solve for the charge of copper, which would be +1. And so this would be called copper 1 chloride. Next we have HGO. So again, you may not know anything about mercury, but you should know something about oxygen. And oxygen has a -2 charge. So since we have one oxygen that's -2, we can set up this little equation and solve for the charge of oxygen. Copper. Mercury. Long day. So mercury is a +2, so this would be Mercury 2 oxide. It's very important that you put the Roman numerals after the metal. Just to let you know, you only need to know your Roman numerals up to 7. So 7 is the highest charge you'll probably ever encounter. Next we have Fe2O3. You may not know anything about iron, but you should know something about oxygen. Oxygen is -2, and we have 3 of them, and they have to balance out 2 of the cations of iron. So in order to do this, we have a charge of +3 for iron. And this is called iron 3 oxide. MnO2 for oxygen, again, -2, and we have 1 manganese. So here it tells us that manganese needs to be a +4. So we have manganese 4 oxide. I like oxide for some reason. And then PbCl4, you may not know anything about lead, but you do know about chloride. So chloride's a -1. We have 4 of them. That means lead is a +4. So this is lead 4 chloride. So again, if the point I'm trying to stress is that you don't have to memorize all the different transition metal charges. As long as you know the anions, you can determine the cation's charge. So this is referred to as the systematic naming. Now we're going to look at what's called the common naming for metals that only have two cations. And I believe it's table 2.4 in your textbook. If you take a look at that, it gives you some of the common metals that we use for this common naming scheme. And again, they only have a high charge and a low charge. And so instead of using a Roman numeral, if it's the high charge present, we put ic at the ending of the cation. If it's a low charge present, we put OUS as a suffix on the cation. Again, this goes on the cation, not the anion. And all of these cations have to have, or all these elements have to have a high charge and a low charge. And a lot of these elements, we use the Latin name. So for example, if we're going to use this naming scheme or common naming method, things like copper, iron, gold, tin, and lead, they use the Latin name for this. Let me write those up here. I believe that's all of them. I can't. Yeah. So if it's one of these elements and you want to do the common naming method, if you use copper, iron, gold, tin, or lead, they use the Latin name instead of the systematic name. So we talked about copper 1 chloride. You see here that copper 1 is the lower charge of copper. So that would make this cuprous chloride because the Latin name of copper is cuprum. So if you want to use the common naming method, it would be cuprous chloride. Next we have Mercury Two Oxide. So mercury can either be a +1 or a +2. Now with mercury, even though it has a Latin name, we use the systematic name when putting in the suffix either ic or ous. And since mercury is a +2, it's the higher charge. It would be mercuric oxide. With Fe2O3, iron 3 oxide, the 3+ is the higher charge. So here we use the Latin name. It becomes ferric oxide, commonly called rust. Next we have PbCl4, lead 4 chloride, so we're using lead. The 4+ is the higher charge. Now lead is one of those that I mentioned you have to use the Latin name. So the Latin name of lead is plumbum. And so this would be plumbic chloride, not oxide. Let me correct that. Now we have cobalt 2 sulfide. Just to make you, there's a correction here. It should be COS. There shouldn't be any 2. Let me get rid of that. So cobalt 2 sulfide, we're using the lower charge of cobalt. And so for cobalt, it doesn't have a Latin name, so this would be called cobaltus sulfide. So again, this is called the common name versus the systematic name that we had on the previous slide. Both ways are acceptable. Usually when you go to a chemical, like you want to purchase chemicals, typically they have the common name, not the systematic name. Sometimes they have both, but a lot of times they'll just have the common name in the catalog. But again, these are only for those transition metals with a high charge and a low charge. So now I have a few examples I want to go through, and I have a periodic table, so I can maybe help as a reference. So we want to write the formula or the name for the following ionic compounds. So we look at our first example, we have Cu3N. And so Cu is copper, and N is the anion nitride. Well, Cu is a transition metal, and it's not one of the transition metals that has one charge, so we have to determine the charge of copper. And so if we look, we know that nitride is in group 5, it's going to have a -3 charge. So we set up our equation, we have 3 copper ions, unknown charge, plus 1 nitride with a -3, and this has to equal 0. And so we get that X equals a +1. So this would be called copper 1 nitride, or you could say cuprous nitride. Both are accepted. Next we have plumbous sulfide. We have to write the formula. Well, we know sulfide is an S2- because it's in group 6. 6 minus 8 is -2. Now for plumbous, the OUS signifies that we are using the lower charge of lead. And maybe you're not familiar with that yet, but the charges of lead are +2 and +4, just like tin. And so if we're using lead and it's plumbous, that tells us that lead is 2+. So since lead is 2+ and sulfide is -2, this would be just PbS. So that's the formula of lead 2 sulfide. Next we have our auroric phosphide, and aurorum is the Latin name for gold, and we have phosphide. So phosphide again is in group 5A, 5 minus 8 is -3, so we know that phosphide has a -3 charge. Now auroric is gold, and since it has the ic here, it's signifying that it's the higher charge. Now for gold, the two charges are +1 and +3. So since it has the ic at the ending, this tells us that we're going to be using gold +3. And since gold has a +3 charge and phosphorus has a +3 charge, this becomes AuP. Now we have a compound, we want to write the name. So we have a cation, zinc, and the anion is oxide. Now the question is do we need a Roman numeral for zinc? And the answer is no. Zinc is one of the 4 that we mentioned early on that has 1 ionic charge. So the correct name for this compound is zinc oxide. This is probably one of the most commonly missed compound naming questions every semester. Because again, zinc, silver, cadmium, scandium only have 1 ionic charge. And then lastly, we have Cobaltic Selenide. Now selenide is selenium. Selenium is located in group 6. 6 minus 2 is -2. or not 6, 6 minus 8 is -2, so selenium has a -2 charge. Now cobaltic is cobalt, and the ic signifies that it has the higher charge. And so cobalt can be a +2 or +3, just like iron and nickel. So since it's the ic, it's the higher charge, so we're looking at cobalt +3. Now, a neat thing you can do here is if you know you have cobalt +3, selenium's -2, we call it the crisscross. You take the charge of each, and they become the subscripts of each opposite ion. And so this becomes CO2 S3, Se3. Now this crisscross is it works most of the time. The only thing you have to watch out for is to make sure that the common multiple between the subscripts is 1. If it's not, you need to factor out what the multiple common factor is until you get a common multiple of 1 for your formula. So anytime you're at a ionic compound, generally it's going to have a common multiple of 1 between the subscripts. So for example, if this was 4 and 6, you would factor out a 2 to get 2 and 3. So far we've been talking about monoatomic ions, ions that only have one type of atom in the formula. Now we're going to expand and talk about polyatomic ions. Now the difference between those is that polyatomic ions, the ion has more than one type of element in the formula. Most of them contain an element plus oxygen, which we'll find out that those are called Oxo Anions. So naming with polyatomic ions, we have polyatomic cations and polyatomic anions. And again, these are charged species with a bunch of different types of atoms bound to it. So previously we just talked about, for example, oxide, which just has oxygen, or fluoride, which just has fluorine. Now you see on this page that we're talking about ions that have maybe, for example, nitrogen and hydrogen, or phosphorus and oxygen, etc. And there is an extensive chart on table 2.5 in your book that you should refer to, and you should be familiar with all the ions that are shown here. Now for polyatomic cations, there's only 2, and so those are very easy, because we'll spend most of our time with the anions. Polyatomic cations, there's only 2. One of them we use in Gen Chem 1, the other one is very seldomly used, but we have Nh4 plus, which is the ammonium cation made up of nitrogen and hydrogen, and Hg2, how do I write this? 2 plus, which is called the Mercury 1 cation. I'll put it in parentheses so that you know. The charge of ammonium is +1. The charge of Mercury 1 is +2. Then the reason it's called Mercury 1 is because you have 2 mercury ions, each one having a +1, so overall it's a +2. These are the only 2 polyatomic cations that the majority of Gen Chem students will ever encounter in chemistry. What we're going to spend most of our time on are oxoanions. So oxoanions have anions that have an atom of one element and then a bunch of oxygen atoms. And most polyatomic ions are oxoanions. And so we have a couple of different families or groupings of oxoanions. There are some oxoanions that have a series where there are 2 members in the group. For example, with sulfur and oxygen, if I was to draw a chart, let's see. We'll do nitrogen, sulfur, phosphorus, and then this is the number of oxygen atoms. So this O is oxygen atoms. We have 2, 3, and 4. And so for sulfur, sulfur is a family of 2 where it has 1 ion with 3 oxygen and 1 ion with 4 oxygen. So what we do is to name the oxo anion, if we have SO4 2-, S is if the anion of S is sulfide. If we drop the ide and we replace it with 8, and that's where the sulfate ion comes from, because it has the most oxygen out of the 2. So when you have a 2-member series of oxo anions, the one with the higher number gets the suffix 8, the one with the lower number gets the suffix I. And so what we do is we take the anion of the non-oxygen part, drop the IDE, and replace it with 8. So now this is sulfate because it ate too many. On the other hand, we have SO3 2-. Again, we start with sulfide. That's the anion of the non-oxygen component. We drop the IDE, it becomes sulfite. And this is the same naming you would use with nitrogen and phosphorus. Now with nitrogen, it has a 2 oxygens and 3 oxygen pair. There's no 4 oxygens with nitrogen. It's only 2 and 3. And with phosphorus, we also have 3 and 4 oxygen pair. Now the charge of the phosphorus oxoanions are -3. So for example, PO4 3-, or PO3 3-, and PO4 3-. So for phosphorus, just like phosphide has a -3 charge, PO3 and PO4 both have a -3 charge. For sulfur, just like sulfur has a -2 charge, sulfate and sulfite have a -2 charge. Now with nitrogen, and it's kind of neat here, if you look at the trend, phosphorus -3, for oxoanion, sulfur -2, nitrogen is actually -1. So when you have, and I'll write them over here to the left, NO2- and NO3-. So again, in the oxoanions or oxyanion series, the ones with phosphorus have a -3 charge, sulfur with -2, and nitrogen with a -1. Most of the other ones we encounter are either going to be -1 or -2. Now there are some oxoanions or oxyanions that have a family of 4, and these are going to be the ones that have a halogen attached to the oxygen. So if you see a halogen attached to an oxygen, it's going to have a family of 4. And so we have a difference between the high and the low. So for the 3 oxygen and 4 oxygen, they both get the ending 8. But to separate them, the one with the most oxygen gets the prefix per. So whenever you see perchlorate, per means it's going to have the most oxygens, which is 4. Chlorate means it's only going to have 3 oxygens, because the boundary between high and low is between 3 and 2. Now 2 oxygen has ite. To separate the 2 and the 1, we use the prefix hypo for the 1. And whether or not we get to naming acids, but knowing the names of the polyatomic ions makes it real easy to name the acids of those ions. And the same would be for bromate, which is BrO3, or the bromine series, and also the iodine series, which is, iodate would be IO3. And for all of the halogen ones, oxoanions have the same charge as the halogen itself, or the halide, which is -1. And again, the best way to remember these is make some flashcards. On one side have the formula, on the other side have the name, and just go through them over and over again till you know. It'll make your life a lot easier when you know these, because naming acids will be very straightforward. So this is just showing you some of the common polyatomic ions. Again, refer to your table in your book for a more extensive list. But as I said, polyatomic cations, ammonium is more common than Mercury 1. And then we have the 2 nitrogen series, the 2 sulfur series that we mentioned. And then over here, well, they just show phosphate over here. There's also phosphite, but phosphite is not as common as phosphate. Now with sulfate, sulfite, and phosphate, phosphide, and even carbonate, you can add a hydrogen to it. So carbonate is CO3 2-. Hydrogen carbonate is when we add an H to it. So HCO3 is hydrogen carbonate, or sometimes referred to as bicarbonate. Carbonate is CO3 2-. The same thing goes with the sulfurs. If you add an H to sulfate, it becomes hydrogen sulfate, or referred to as bisulfate. You can do the same thing to sulfite. You can say hydrogen sulfite when you add a hydrogen to SO3 2-. Now with phosphate, since you can add up to 2 hydrogens for it, it doesn't use the bis or the bi prefix. It just is hydrogen phosphate and dihydrogen phosphate. Some other ones, we have cyanide, which has no oxygen in it. And then we have, and these are some not to get confused, we have chromate is CrO4 O4 2-. So notice chromate is not perchromate, it's just chromate. It's not a halogen. And then we have dichromate as well. So now we're going to look at some examples involving polyatomic ions. So here we're given either the name or the formula. We want to write the ionic compound. Now I know some of you may not know the polyatomic ions like I do, so for the time being you can refer to a chart, but as you get more and more practice with it, some of these will become second nature like they are for me. So first we want to look at the first one. We have nickel 3 sulfate. So the 3 implies the charge of nickel. So let's go ahead and write that. We know that nickel is a +3 because the Roman numeral tells us it's a +3. So that makes it easy. Now sulfate, if we can deduce the name, we can write the formula. So sulfate means we're going to use sulfur. So we're going to need an S. And 8 means it's going to be the higher number of oxygen. And so sulfur can either be 3 oxygen or 4 oxygen. So it's going to be 4. And the oxo anions with sulfur have the same charge as the monoatomic anion sulfide. So it's going to be -2. So what we can do is, now that we know the charge of each ion, we can do a crisscross. So the -2 becomes 2 for nickel, and the 3 becomes 3 for sulfate. And we can write the formula as Ni2. Now, since we have more than one polyatomic ion, we have to put it in parentheses, SO4, 3. And so that's the formula of nickel 3 sulfate. Next, we have a formula. We want to give its name. So here we have CD is the cation, so CD stands for cadmium. So we got that, check. Now we have the anion HCO3. Now we know that the anion CO3 is carbonate. But since we put an H there, this becomes hydrogen carbonate. Or we could write cadmium, and since it's carbonate, we can put bicarbonate. Both are acceptable. Now the question is, and this is the important question, do we include the charge for cadmium? And the answer is no. Cadmium is one of the 4 transition metals that I said had only one charge. So the answer is, or the name is cadmium hydrogen carbonate or cadmium bicarbonate. So either name is acceptable. Moving to the next example, here we have SnClO2, 2. So the anion here is ClO2, so it's an anion that has a halogen attached to it, and it only has 2 oxygen. So since it only has 2 oxygen, it's going to have the ending ite. So this is chlorite. It's not hypochlorite because hypo means it only has 1 oxygen. So ite means 2 oxygens. Hypo in ite means 1 oxygen. 8 means 3 oxygen, and per and 8 mean 4 oxygens. Now Sn is 10. And the question we have to ask ourselves, do we need to indicate the charge of 10? And the answer is yes, because 10 is one of those that has multiple ionic charges. And so one easy way to do to determine the charge of the cation and the anion is to do the reverse crisscross, which works most of the time. Not all the time, most. And so if we do that, we see that 10 is a 2 plus, and chlorite is a negative 1. Negative 1 plus 2. And so this becomes 10, 2 chlorite. Or we can write it in its common name, and since 2 plus is the lower charges, we stannous chloride. So either one is acceptable. The next example, we have barium chromate. So barium we know is group 2. It's Ba. 2 plus. Now chromate will be one of those that you just have to, you'll get more familiar with as you do more practice, but chromate is CrO4 2 minus. Now if we do the reverse, or we do the crisscross, you see that now we get that the formula is Ba2 CrO4 2. But notice that the common multiple in the subscripts is not 1, so then we're going to factor out the 2, and we get BaCrO4. And so that is the formula of barium chromate. Next we have ferrous cyanide. So ferrous comes from the Latin name ferrum, which is iron. So one of our cation is iron. Now cyanide is the only anion listed in the polyatomic ions where you have a anion does not have oxygen, and cyanide is Cn minus. You've heard of cyanide poisoning? That's where it comes from. Now we have to determine the charge of iron. So you see here we have the suffix ferrous. Ferrous indicates the lower charge. And so iron can either be a +2 or +3. So since it's OUS, that indicates that we want the lower charge, which is +2. So now we do the crisscross, and we get the number of each. Now if it has a subscript of 1, as you notice, we don't include it in the formula. So this would be FeCN2. Again, if you have more than one polyatomic ion, you have to put it in parentheses and then the number outside the parentheses. Next, we have the formula Nh4 Mno4. So here you have to be careful. Nh4 is a polyatomic cation. And this is probably the most common polyatomic cation, which is ammonium. Now the anion is MnO4. And you may say, hey, it has a 4 there on the oxygen, so it needs to be, for example, permanganate. And the answer is, that's right, because this 4 here, so there's different rules for different ions. So here we have MnO4, and let me write the formula for that so you can see it. MnO4 is a -1 charge, just like ClO4 is a -1 charge. So since MnO4 is a -1 charge, just like ClO4, we put the prefix per, and this becomes permanganate. So that's the name of this ion. But it's the only non-halogen oxoanion that gets the prefix per. And so this becomes ammonium permanganate. Lastly, we have Mercury 2 hydroxide. So the 2 indicates the charge of mercury. So we know that's Hg2+. Now hydroxide means you have a hydrogen attached to an oxygen. So typically we write it like this, OH minus. Now if you add another hydrogen to hydroxide, guess what you get? You get H2O. So now we have hydroxide, OH minus. We do the switcheroo. We get HgOH2. So Mercury 2 hydroxide. And so again, you know, it may look, I know it looks like it's easy, but again, as you practice and you become familiar with the names of the polyatomic ions and their charges, it becomes very straightforward on how you name these compounds. I tried to give some tips to kind of help you deduce the formula from the name, but the best way to do it is just to know the polyatomic ions so that it'd be easier when you see it to know the name and its charge and its formula.